In today's lesson, we're going to look at rational or applications of rational functions. Rational applications are scenarios that can be modeled by rational functions. So there's just a couple of examples to go through, and we're just going to use what we know about rational functions in order to simplify them for the most part. And of course, that's going to involve factoring. So let's get to it. The area of Randy's backyard is represented by the expression 3x equals 3x over 4x squared minus 9. Randy has a shed in his backyard that occupies an area of 4x over 6x squared plus 13x plus 6. So again, these are both areas in each case. If I want to find a simplified expression for the area of the grass that Randy needs to mow, that would be all of this, right? The shed is the little white area, and the rest of it's grass. So if I want to find a simplified expression for the area that Randy needs to mow, then it's going to be a subtraction to start with. So I'm going to let m of x represent the area to mow, and it's going to, start with the area of his backyard, which is 3x. And I'm going to take away, 3x over 4x squared minus 9. And I'm going to take away the area of the shed, which is 4x over 6x squared plus 13x plus 6. Now, in order to simplify it, of course, we know what we have to do. We need to factor it so that we can then get our lowest common denominator and then combine this into a single fraction. So I recognize that the first denominator is a perfect square, difference of squares binomial. Factor of the first term is 2x. Factor of the second term is 3. My goodness, so many slips of the tongue. Hopefully I got them all out of the way. And difference of squares means I'll put a plus sign in one of the brackets and a minus sign in the other. So that's my factored version of the difference of squares. Factoring the other part is one of the more complex trinomials. It's got a 6, it's got an a value of 6 out front here, which does not common factor out. So I'm going to have to try one of my techniques for factoring more complex trinomials, such as trial and error or decomposition. I'm going to go with trial and error. So when I do trial and error, again, I take two factors that are as close together as possible, say the 2 and the 3. And if I were to go do the 6 on the other end, so I'm breaking down this factor here, this term here into those two factors. If I want to break down this term into two more factors, I think 2 and 3 would be good choices, because if I multiply the corners together, what I would get is 3x times 3 is 9x, 2x times 2 is 4x. That's going to add together, give me the 13x in the middle. So if I make these both positive, it looks like that fits all the criteria for my factors. So I would have 3x plus 2. I'd have 2x plus 3. And lucky for me, I've already got 2x plus 3 in the other denominator. So when I want to get a common denominator, I don't need to duplicate that 2x plus 3. It's already there. I just need to multiply the top and bottom of the second fraction by 2x minus 3, and the top and bottom of the first fraction by 3x plus 2. So let's do that. That means I'm going to do 3x times 3x plus 2 over 2x plus 3 times 2x minus 3 times 3x plus 2. Just to highlight to show where everything's coming from and where everything's going. Those are the factors. I highlighted each factor in a different color. Those are the factors in my lowest common denominator. And I had to add the 3x, or to multiply the top and bottom by 3x plus 2 to get that 3x plus 2 into that first denominator. Likewise, in the second denominator, I'm going to have to multiply the top and bottom by 2x minus 3 to get myself a common denominator. I'm going to put them in the same order as well, the factors. And 3x plus 2. So I just rearranged the order a little bit, but I've got the same factors. And so now I've got a common denominator. I can simplify the numerators by doing distributive law. And when I do that, well, you know what? Maybe I won't do that quite yet. Maybe what I'll do first is just bring them together into a single fraction. So 3x times 3x plus 2 minus 4 times 2x minus 3 just so that I've got them all together into a single fraction first. Now I'll do the distributive law, now that everything's brought together. And I'm going to multiply everything in the second bracket by negative 4. So when I do that, I get 9x squared plus 6x minus 8x plus 12. Of course, nothing's happening on the denominator now. I just keep writing it down for consistency's sake. But then I'll collect my like terms, and I have 9x squared minus 2x plus 12 all over the same denominator. And I should look to see if I can factor the numerator, but I don't see anything that common factors. And as far as thinking of factors of things, well, I don't think it's going to be possible to find two numbers with the same signs that would multiply to give 12 while at the same time adding to give a negative 2. Of course, anything's possible, but I'm fairly confident that that's not going to be factorable. So my final answer would be this. This is my simplified version when I brought the two rational functions together. Determine the simplified expression for the base of the triangle, given that it has an area of 9x squared over x squared minus 14 plus 45. I think that there should be an x in here. I'm going to go out on a limb and assume that that's a typo and there should be an x. Otherwise, why would anyone have written it like that instead of just saying plus 31? So let's assume there's supposed to be an x there. And here's an expression for the height of the triangle. If we put that together with our knowledge that the area of a triangle equals base times height divided by 2, then I can fill in some blanks. I can have 9x squared. Do I want to do it here, though? Maybe I want to do it over here where I've got a bit more space. So I'm going to go 9x squared over here over x squared minus 14x plus 45 equals base, which is what I'm trying to find, times height, which is 3x over 5x minus 45, and all over 2. Okay, so I need to isolate the base, right? So I could multiply both sides by 2. So if I do that, the 2's will cancel out on this side, and I'll have 2 times, I don't want to do a times sign like that, do I? Because it looks like an x. 2 times the 9x squared. So that's how I can get rid of the 2. And as far as getting rid of this, I could invert and multiply. So I could multiply both sides by 5x minus 45 over 3x. So that's what I'm going to do. So Simplifying the left first, I've got 18x squared over x squared minus 14x plus 45. And then if I multiply by the reciprocal of 3x over 5x minus 45, I'll have 5x minus 45 over 3x. And we're going to multiply these together equals b. And then I can start reducing. Maybe what I should have done before I even got started was to try and see if there was something that I could factor in this numerator or this denominator here. 45 could be 15 times 3, but that doesn't help. Or it could be 9 times 5. That sounds promising, doesn't it? So why don't I rewrite that one since we've already got it up above. Let's rewrite this as x minus 9 times x minus 5. Negative 9 times negative 5 is going to give me positive 45. Negative 9 plus negative 5 will give me the negative 14. So that's all good. Whoopsie. And why don't I factor this while I'm at it too? So I can take 5 out as a common factor and I'm left with x minus 9. Because that's convenient. Look at this here. I can cross out this x minus 9 and this x minus 9, anything in the numerator with anything in the denominator. I can reduce 3 goes into itself once and 18 6 times. And x goes into itself and it cancels one of the x's on the top. And so what I'm left with when I multiply it all together is I've got the 6 and the 5. I've still got this 6 and this 5 that I have to multiply together and this x, right? So that's going to give me a 30x in the numerator. And in the denominator, all that's left is x minus 5. And that's what's equal to b. That's the expression for the base. Question answered. Boom. Okay, so we're just going to use our techniques of simplifying rational functions. The only thing that's really new in these applications is that we are creating our own expression by adding, subtracting, multiplying, or dividing rational expressions based on what the word problem tells us.